Today I'll talk about this topic called quantum paper, and more specifically I'll talk about how to design fiber and network for lightweight composites. So as a start, why are we really targeting and focusing on lightweight? Currently the transportation fuel is the biggest contributor to the carbon dioxide emissions, or in other words the carbon footprint. And in that regard, cutting the weight in all types of transportation is extremely crucial. So, what do we really mean by saying lightweight composites? If we consider this aircraft here, the development has been going on to reduce the weight, both when it comes to the material itself that we use in the aircraft, but also when it comes to the structure, how you structure the material. And the center of action when it comes to material development is all about reducing the weight, and therefore this also creates a lot of air in the structure. So, moving on to looking at the product that's actually produced in our region. As you might all be aware of, this is then corrugated boxes, which is used for transportation of all types of products. This, if we go into a bit closer when it comes to the structure of these boxes, we can see we have a corrugated structure here, and this is a great example of lightweight composites. And this composite, if we go even further, we can look at the structure of the material itself. So this is then an illustration of a fiber network, which is then called paper. And this structure also includes a lot of air, making it very light. So you can actually say that this is also an example of a lightweight material. Just as an example here, when you look at this picture, we have a wood pallet here. And this wood pallet is actually quite heavy if we compare with these composites that I'm talking about. So right now people there are trying to replace these ones with much lighter honeycomb versions out of these pallets. Just as an example. This leads us to the next question of how can we then design these composites? And the hard thing with this is we want to keep the performance at the same time as we reduce the weight, and that's a big challenge. The answer that we have for this question is that we need to consider the structure. So this is then good examples of lightweight structures. They are very light, but at the same time they are also extremely light. When it comes to how we develop these structures today, most structures are actually developed by the computer. And this is then the best way to find the best design, as well as also find unique performance properties. But what do I really mean by saying performance? Because that can differ depending on who you're talking to. In our case, for structural composites, of course, it's extremely important for them to be very strong. At the same time, we want them to be durable. We want them to last as long as we wish. And lastly, we also want them to be reliable, that they will perform as we wish, time after time. And among these parameters, strength is something we have measured for quite some years. But when it comes to these two, durability and reliability, it's a bit more tricky how to evaluate these performances. So this is what we tried to find a method to do. So what we want to evaluate is something like this. This is a paper structure. And we want to find these parameters, strength, durability, and reliability for this. And that's a bit challenging. I'll try to just briefly explain how we try to do this. So we will want to find these parameters and what's controlling these parameters. So what we did was in the computer, we started to construct a network based on these coordinate points. Between these coordinate points, we put elements, which we then call fibers. And this is then what we refer to as quantum paper, because this is a discrete system, and it can be seen as a simplification of the fiber network, as I showed you in the previous slide. So what we did with this is then that we performed so-called Monte Carlo simulation of this network in order to then find these the fiber characteristics for this structure. So you may wonder why I just showed you this very nice and regular structure, because in real life, and also when it comes to nature, nothing is really perfect. So what we did was that we tried to create this random structure, looking something like this. And then we put it together. So what we did was that we distorted these points from its original position and then put it together to a network. So that's also something we tried. So I'll just shortly try to highlight some of the results, because we have performed these tests for network to find these parameters, as I mentioned. And why we do this is also in order to know and find clues. What can we do? What can we change when it comes to the design of the material? But also, what can we change when it comes to the manufacturing processes? So this is an example of animations of this network for two different types of fibers. We have ductile fibers and brittle fibers. So as you can see here, these points here represents the fiber breaks. So the difference between these two is that it requires much more fibers to fail in this case than in this case. And that might be a question, okay, what's good? It depends on the end use. But what do we want to use these products for? Is it really important that it's not really, for example, if you have a defect in this one, then it might be very fragile. So then it might be better with this one. So it depends on the end use. When it comes to these computer-based methods, the big benefit is that we can repeat the test several times. So we have performed this thousands of times, and that's not really possible when it comes to real experiments. But we are also performing real experiments in order to validate these results. So that's something we're doing simultaneously. Just briefly, I'll show you here how this reliability parameter is affected by the randomness. And with randomness, I mean how much the structure is distorted from the original. And as we can see here, with increasing this randomness, the reliability goes down. At the same time, we can see that we have two different types of fibers. We have ductile fibers and brittle fibers. And we can see that with brittle fibers, they are much less reliable. So meaning that depending on the input fibers, we will have a difference in this reliability parameter. So this is 2 slides. So this is just some results for the durability parameter, and we can say that the durability for the whole network is fully determined by the durability for the fibers itself. So this again tells us that the fibers, they are important. So last slide here is that I just want to emphasize that we think that these lightweight composites can be used for several different applications, and in that way I think we can somehow redefine the future of paper. Thank you.
Thank you very much, Amanda. Do we have some questions from the audience? Please. Don't be shy.
It's too complex.
Yeah, complex materials. Yeah. Okay.
What kind of applications do you see for that type of fiber?
This type of fibers. I think, for example, when you consider carbon fibers, glass fibers, all these types of applications, so far we just put glass fibers, carbon fibers for many of these applications, but I think it's possible to replace some of it, because if we look at the properties of the fibers, they are extremely strong, especially if you consider the weight as well.
Yeah, when you talk about discretize the model in small nodes and fibers, do you consider also like boundary condition between all components happening, and also when you limit it to a size?
Yeah, actually this is not, we're not applying periodic boundary conditions, because we're interested to see the size effects, so we can have a discussion afterwards how I put out the system.
Thanks.
Okay.